Thanks for tuning in and wanting to learn about active heat recovery. My name is Mike Jenin. I work for Advanced Industrial Refrigeration, and AIR are really experts at refrigeration or compressorized equipment. And my role is servicing the Canadian market with new and innovative ideas that are unique to cold climates. As many of us know, Canada is certainly a cold climate, and most of the time we are heating dominated, and heat recovery has become a talking point, certainly when we talk about chillers, heat recovery chillers, heat pumps, geothermal, and other technologies. But today we're going to talk about ventilation heat recovery and using active heat recovery as a form of energy savings on the ventilation side. Most heat recovery that exists today is passive heat recovery that exchanges heat from one airstream to another, but I will show you today how active heat recovery using a refrigeration circuit to exchange heat between two airstreams can reduce greenhouse gas emissions and improve operational cost savings at the same time. So when we talk about energy use in buildings, this graph here is from Natural Resources Canada. You can see that in terms of energy use in large residential and commercial buildings, the vast majority of the energy is spent on heating. If you were to look at data from the United States, the amount used for heating would be approximately 30%, and there would be more attributed to cooling. But in northern climate, heating is really the bulk, vast majority of the energy use in the building. And about 30%, give or take, of this heating is spent on ventilation. And that is a significant part of the overall energy use and energy costs in the building. And that's what we're going to focus on in this presentation today. Improvements in efficiency in this sector can lead to large ROI and a large reduction in greenhouse gas emissions as well. Speaking about greenhouse gas emissions, cities really lead the way in terms of at least the planning to reduce greenhouse gas emissions. This data is from the city of Toronto. Many other cities have similar, if not almost identical, targets to reduce greenhouse gas emissions. In this graph, by 2020, we have a 30% reduction in greenhouse gases, and by 2050, an 80% reduction in greenhouse gases. The greenhouse gas emission reduction policy has really become a priority, and ventilation heating is a significant source of greenhouse gas emissions when it comes to buildings. If we're going to hit the target of 80% reduction by 2050, you need to keep in mind that by 2050, most of the buildings that will exist at that point already exist today. And so ventilation retrofits are going to be an important priority that needs to take place. And ventilation system is an ideal system to retrofit in most buildings. Again, talking about greenhouse gas emissions, this snippet is from the Toronto Green Standard, just using as an example. What happens is not only do we have goals to meet greenhouse gas emissions, but we stipulate certain designs or activities that need to happen in order to reach those goals. And just to draw your attention to where the energy savings really starts to occur is where the recommendation of moving away from condensing boilers to an air source heat pump system. really helps with the energy efficiency and greenhouse gas reduction. In this case, in the final tier of this system is an example. They are advocating for a 90% air source heat pump with electric top-up. And the reason for that is the grid here in Ontario is fairly clean, and moving to electrification on a lot of items is become the priority. And so when we talk about electrification, we really need to stop and think about what is the most effective use, an efficient way to use that electricity to generate heat energy. Air source heat pumps have really become the talk of the town these days, and essentially what they are is what we think is a chiller, but in reverse. They're a refrigeration cycle, and just like every other refrigeration cycle, they move heat energy. In this case, they're moving heat energy from the ambient air and using it to generate hot water. And I've laid out a couple performance points there for an air source heat pump, making 140 degree hot water. With 140 degree hot water, you can achieve your space heating needs and achieve perhaps your domestic hot water production. So as you can see, as the ambient temperature moves from, let's say, a design condition of -10 Fahrenheit up to 32 Fahrenheit or so, the COP, or coefficient of performance, gets better. And what that essentially means, if you have a COP of 2 at your design condition, for 1 unit of electrical input, you're getting 2 units of heat. So it is essentially twice as efficient as using just straight up electricity as a source of heat. And that's really why air source heat pumps are becoming more popular. And if you look at this snippet from the Toronto Green Standard, they're calling for an air source heat pump plant with a COP of 4.15. And as you can see, the efficiency gets better as the ambient increases, and this COP of 4 might be reasonable on a seasonal average, and that just means an average of the efficiency throughout the season, weighted by how many hours are spent at each temperature. So air source heat pumps are really becoming more popular. The COP you can expect is about 4. If you're considering using them for energy savings, greenhouse gas emission reductions, we really should consider what we're going to talk about in this presentation, which is active heat recovery. And we'll talk about that shortly. So to talk about active heat recovery, first I want to talk about regular make-up air units to introduce the technology. And in this case, we have a straight up make-up air unit. And what is happening is fresh air is being brought in at our design condition at -4 Fahrenheit. And we are burning 883,000 BTUs per hour of natural gas. In this case, this is for a system that's 11,000 CFM. And we've decided on having a supply temperature of 70 degrees Fahrenheit as our design of room neutral air. So what has become popular in terms of energy savings when we talk about make-up air units is passive heat recovery. And these things might exist in the form of a heat wheel, which is basically a rotor that brings heat from one airstream to another. There are also heat pipes, which are tubes with a small amount of refrigerant, and they move heat from one airstream to another by depending on the change of state in the refrigerant. And then there are also, another common one, are fixed plate or energy cores. And these are the most simplistic example where the two air streams travel in opposing directions and through alternating plates, and heat is just transferred through those plates between the air streams. And with these passive heat recovery devices, the efficiency has been incremental at best, approaching the upper limit of 100%. All these devices, though, range from an efficiency of 40 to perhaps 80% from a theoretical level. So what ends up happening is, in this example, we're bringing our return air and we're bringing our supply air at -4 and running it through the heat rotor and achieving 29 degrees. And what happens in all these examples of passive heat recovery is we still need top-up energy. So in this case, for the same example of 11,000 CFM, we are burning now 500,000 BTUs of heat energy. So to go beyond this level of efficiency, we really need to take advantage of the exhaust. And what's happening here is the exhaust is still 37 Fahrenheit. So to go beyond this technology, we need to extract more energy from that exhaust to break the barrier that limits traditional passive heat recovery. So what active heat recovery does is uses a refrigeration system. Just like any other refrigeration system, it moves heat energy from the evaporator, and the compressor upgrades that heat, and it discharges it into the condenser. And that same principle applies when we're talking about the fresh air active heat recovery unit. We bring our return air back from the building into the evaporator, the cooling coil, and that air is cooled down to the exhaust temperature, and the compressor sucks the heat out of that evaporator coil. Then the compressor compresses this and discharges it to the condenser coil or the heating coil. And then this allows us to bring our outside air stream across that condenser and heat it up to the desired supply temperature. So in this example, the fresh air unit is able to heat the supply air to our desired 70 Fahrenheit with a return air that's also at 70 Fahrenheit with no top-up energy required. This is critical because we don't need top-up energy that's derived from electric or other fossil fuel sources, which can help us achieve our energy savings and greenhouse gas emission reductions. Also, the seasonal efficiency of this system is about 7. So when we compare back to our air source heat pump with the seasonal efficiency of 4, we now have a system that's nearly twice as efficient on the ventilation side. And where that stems from is if you look at the exhaust temperature, which in this case is 20 Fahrenheit, our exhaust temperature is still warmer than our outdoor air conditions. So of course it makes more sense to extract heat energy from that exhaust rather than attempting to extract it from the ambient in these conditions. Another advantage of heat recovery is overdrive mode. And I've chosen a supply condition here of 75 Fahrenheit. I'm running the refrigeration system a little warmer than normal. And what that does is it offloads the heat from your central plant and puts it onto your ventilation unit. So as we discussed, the fresh air or active heat recovery has a COP of about 7 seasonally. Let's say you have a central gas heating plant? Well, depending on the cost of gas, it's typically about 3 or 4 times less expensive to heat with gas and electricity, so a ratio about 4 to 1. Well, the active heat recovery has a COP of 7. So by running it harder, you can actually offload some of that energy from your natural gas plant and put it on your ventilation unit, resulting in both costs and greenhouse gas emission reductions. Let's say you have an air source heat pump plant as your central source of heat. Well, back to our discussion, the average seasonal efficiency of that is about 4. And given that active heat recovery has a seasonal efficiency of 7, that can result in even further energy savings and cost reductions. So these are really the direction that we need to be headed in terms of heat recovery on the ventilation side, is talking about, again, extracting as much energy as possible from that exhaust to produce as much heat as possible to break the barriers of traditional passive heat recovery. So we've plotted outdoor air temperature with the efficiency COP for active heat recovery. And the efficiency varies greatly with the outdoor air temperature, down to a design condition of -4 that we've been talking about. You can expect a COP of around 4. And on more mild days, when you approach 50 Fahrenheit, you can expect a COP of 12. And the reason for that is, if we think of let's say a conventional chilled water system or a chiller, when you talk about part load efficiency of the chiller, or NPLV, the efficiency of the chiller gets better when the ambient condition or your condenser water cooling tower relief occurs, when you have part load on the compressor and part lift given by cooler ambient conditions. And it's the same analogy with the active heat recovery, given it's a refrigeration system. When the ambient conditions are colder, I need to extract more heat. The temperature of my exhaust goes down on my evaporator, my suction pressure goes down, and the lift on my compressor goes up, so the efficiency is poor. On a more mild day, I don't need to extract as much heat, and the suction pressure is not as low on my evaporator. The lift or pressure on my compressor is less, and the efficiency is better. And what that results in is average seasonal efficiency. In a Toronto or northern climate, the seasonal efficiency ends up being at a COP of 7. Again, this is a huge improvement over air source heat pumps, and a huge improvement in operating costs when compared to gas heat as well. So how do the operating costs pan out over a whole given heating season? So in this example, using the same 11,000 CFM, we ran the numbers for different situations: electric, gas, electric with passive heat recovery, gas with passive heat recovery, and then fresh air active heat recovery. And the results are as follows, and these are using Ontario electric and gas costs. So electricity by far the most expensive, about, as we discussed, 3 to 4 times the cost effectiveness as burning natural gas. And when we move to the passive heat recovery, you can say they take a sizable dent in the total amount of energy use which is expected. And then we have fresh air active heat recovery, which is about on par with an efficient gas heat source and efficient passive heat recovery device. Where active heat recovery really thrives is on greenhouse gas emission reductions. So we've done the same simulation for greenhouse gas emissions, and as you can see from this graph, that electricity, although more costly, has a sizable reduction in greenhouse gas emissions when it comes to burning natural gas. But by far the best is active heat recovery, and that's because it gets that seasonal efficiency of about 7-to-1. So active heat recovery is really the key that needs to be discussed when it comes to any project concerned about greenhouse gas emission reductions, especially on the ventilation side. And in addition to this, if overdrive mode is taken into consideration depending on what kind of central plant exists or what would exist in a new construction project, active heat recovery can help further offload the amount of greenhouse gas emissions from other systems in the building as well. So the next question is the efficiency of active heat recovery real? And I'm a proponent of real world data. There's lots of technology out there, but the problem is, does it actually deliver what it says on paper? And the challenges of passive heat recovery are things such as fouling of the heat exchangers. We have defrost concerns. In the example of heat wheels, the heat wheel needs an air purge cycle to clean itself as it rotates from one airstream to the other. All these things reduce efficiency and are difficult to represent on paper. So I really like using real world data as a comparison of different technologies. And so this is a great case example. This is a high-rise multi-unit residential building. The system was 11,000 CFM. The existing building had electric heat and was supplemented by a heat wheel. So in terms of an ROI, this is an excellent case example. So what we did was a third party came in and recorded the data from the existing heat wheel electric heat unit for a few weeks in the winter. The unit was replaced and then the fresh air unit was installed. And after the installation, the data was recorded again. So we really have some good real world data on this unit compared to a previous heat wheel unit. And these are the results from the study. If we start with the gray line, no heat recovery, this is where the existing unit was recorded with the heat wheel deactivated. And you can see it's essentially a perfect linear correlation, which we would expect given the amount of heat needed to be added to an airstream is proportional to the delta T. If we move down to the blue line, this is with the heat wheel, the existing heat wheel unit. You can see that the line is not perfectly linear. The efficiency of a heat wheel is not going to be exactly consistent over the full operating range, but we have a substantial reduction in energy of about 40%. I've rarely seen heat wheels operate near anywhere near 80% that they claim, but this was certainly an older model heat wheel. And then in the green, you have fresh air active heat recovery, which is by far lower and delivered in this case example an average reduction of 78%. And you might immediately ask, why is the correlation a little scattered in some areas? Well, the fresh air operates like any refrigeration device with multiple circuits and multiple compressors, and occasionally you have compressor cycling and a compressor rotation, where one of the compressors turns on and that heat is not immediately realized in the supply air stream, and you have small moments, and when the data logger picks that up, you get those small outliers. But it is a substantial reduction in energy, and if we look back at the theoretical model from before, where fresh air had a projected operating cost of $13,000, and we compare it with the straight up electric heat, this reduction of 78% is almost dead on with the theoretical amount of energy reduction. So the last thing we're going to talk about are the side benefits of active heat recovery. And the reason for that is it is a different type of heat recovery that is not commonplace like passive heat recovery. And so there are some other details that need to be pointed out as well. So we've talked about the advantages of energy savings, greenhouse gas reduction, but there are some other benefits that can be extracted. So the first thing is no cross-contamination between the two air streams. The unit is designed for this, and because we don't have a heat rotor or other device where air streams are being switched, you can have a machine with no cross-contamination. And that means that we can now extract energy from sources that were previously unattainable. And we need to start considering these sources if we're going to meet our greenhouse gas emission goals. So non-breathable exhaust or exhaust contaminated with vapors or other fumes can also be considered now. The other question I get asked is, well, isn't this active heat recovery more complicated, more costly to maintain? And just because it's a new concept doesn't mean it is more complicated. In fact, it's quite the opposite in this case. If you think about a comparable DOAS unit, you're going to have a gas heat or electric heat section. You're going to need an energy recovery device like a heat wheel, and then you're going to need some kind of cooling if you want cooling, to compare apples to apples, and that's going to occur as a DX system. That's three systems that need to be maintained. With fresh air, there's only one system, and that's a refrigeration system, which is a huge advantage. The other item we briefly discussed was the part load energy savings. The efficiency of this technology is not linear, but that allows for immense part load energy savings, and to further take advantage of the situations when we have part load is these units are equipped with VFD driven compressors. And that also not only for energy savings, but helps with the turn down ratio. You can often get a better turn down ratio than many gas burners can. And also it helps really dial in the supply air temperature, making sure you're getting a nice constant supply air temperature. And then also direct drive plenum fans have become commonplace, but we haven't talked much about the controls on this unit. You can add a CO2 or total air quality sensor, and the controller in this unit will automatically do a demand control ventilation sequence where it ramps the fans up and down. And then with that, you can realize even further energy savings above and beyond what we've talked about today. Another great benefit of fresh air is that it has a much better footprint. Like we discussed, we only have one mechanical system in this unit to maintain, compared to a traditional unit which would have multiple systems. In this example, we have a unit with compressors, supply and exhaust fan. The heat wheel section is here, and here's our DX cooling. In this case, it has electric supplemental heating. So this is a comparable unit in terms of achieving the exact same performance as a fresh air unit. And it's sized for a certain CFM, and we sized a fresh air for the same amount of CFM, the same amount of cooling, and the same amount of heating. And there is the footprint of the fresh air unit. It is less than half the footprint of a traditional heat recovery unit. That's another great example of how it can benefit and fit in tight installations, so you can recover energy from places that previously were not feasible. And that concludes the webinar. I have some questions I'm going to answer that come in typically. The first is, can it be used for toilet exhaust? And the answer is absolutely. This unit, you can pass many types of different exhaust through it. That's really one of the main advantages, with no risk of cross-contamination. In some very extreme examples, we had exhaust air, for example, that was contaminated with ethanol vapor. Certainly nothing you would want to run through a traditional heat wheel. And we are able to build the exhaust section of the unit spark proof to handle that. Again, another great example of untapped energy sources. Can you give an example of summer conditions? So typically we spoke about sizing in terms of the heating as room neutral 70 degrees. You can certainly go a little bit warmer than that if you need to. In terms of summer, depending on your situation, most of these will be able to cool the air down to about 60 Fahrenheit. If you need to go beyond that, then we can add an auxiliary cooling circuit that can reject more heat directly to the outdoors with an auxiliary condenser. And then you can get your supply air temperature down further than that, and for your dehumidification, if that's a concern. Is it fair to say the supply temperature will be dehumidified in the summer? Again, that depends on your cooling. We can size it to give a 55 degrees kind of a typical temperature for dehumidification. Another great question is with regards to is it adding humidity to the air? Now, a lot of passive heat recovery devices, depending on the technology, not all of them, but some of them can transfer total energy. That means both sensible and latent cooling. So does this active heat recovery, well, it can't transfer latent energy, can it? Well, the answer is yes, it does recover energy from both sensible and latent. If you look at the exhaust or cooling coil, the cooling coil is extracting just like any cooling coil. It is doing both a sensible and latent portion of the load as that vapor in the air condenses in the coil and moves down to the drain pan. So active heat recovery is extracting both sensible and latent energy, and it is better at a desiccant wheel at extracting latent energy, but it is technically converting both sensible latent energy to sensible only energy through the compressor. The condenser coil can only add sensible energy to the supply air stream, and that's an important thing to distinguish, is that you're only adding sensible energy to that supply air stream. Another great question is, are there frost concerns in winter on the exhaust coil? And yes, there are. In terms of the exhaust coil, We have certain defrost cycles to manage the frost accumulation on the coil. It depends on how critical your system is. We can do a couple different options for the defrost. But yes, obviously, when we talk about extracting as much heat out of the system, defrost is a concern. But I can tell you the defrost is far less of a concern on active heat recovery than it would be, say, on an air source heat pump that's extracting from ambient air that is extremely cold. But basically, from field experience, defrost occurs in an extremely cold climate when you have subsequent days that are below, about -10 Celsius. And the defrost, you can expect the defrost in a typical, let's say, apartment building to occur every 4 to 6 hours when you have days that are subsequently cold. In reality, what happens is it gets cold at night, frost accumulates, but not enough to warrant a defrost cycle. And then during the day, when it warms up, that ice just naturally melts. The unit continues as is. So, in a northern climate, you can expect this unit to go into defrost maybe 20, 30 times per year, and that's what our real world data shows. Besides the compressor, is there any supplemental heat source that's required? Not really, unless you want to achieve a really warm supply air temperature. These things can be sized to deliver whatever kind of condition you need on the supply within reason. It's going to depend mostly on your exhaust air conditions. Another great question, what airflow percent can it ramp up and down? In terms of variable air capacity, we talked about the thing being able to do variable air volume or demand control ventilation. It depends on the size of the unit, but as a general rule of thumb, with this kind of refrigeration system, you can expect to ramp the airflow up and down between 50 and 100%. So that should give you a fairly good example. What about heating and cooling? Can active heat recovery switch between heating and cooling is needed? Yes, the fresh air unit, it is equipped with a cooling cycle, and so it can reverse and achieve cooling as needed. And typically you'll have a dead band between heating and cooling, and the controller automatically will make the decision based on the set points that you want to switch between heating and cooling. And another question is, can the unit be placed outdoors? And the answer is absolutely. The majority of these units are designed to go outdoors and be weatherproof. They are available, like in the photo on the screen, in a stacked configuration. Typically those are for indoor use. They just show better on the presentation. And also in a side-by-side airflow configuration that's typically better suited for outdoors where you have more space and it's easier to service that way. So they're available in both configurations. So that concludes the webinar and the questions. If you ever have any further questions, my email and phone are on the bottom of the slide. Feel free to send any other further questions if they weren't answered. And thank you for dialing in and learning about active heat recovery and how it saves greenhouse gas emissions and energy.